So as I started to say in the last video, we're going to talk about assumptions of the ideal gas law. So because it's an ideal law, we are idealizing it, right? We're making it perfect and making it real nice and easy to work with, because the real, like what's actually happening to the gas can be pretty complex. So the ideal gas law, being an ideal law, is a good enough law where we put some certain assumption on there saying if everything worked in this nice, pretty manner, our math would be real easy. And that's what we're going to use mostly in this class. So we have a couple of assumptions that we need to make. So the first assumption we're going to make, which is probably a standard assumption for most things, is this is going to be a classical system, meaning that the particles or molecules or atoms follow Newton's laws. So not a quantum system. All right. So the next assumption we want to make is that the particles are so small they don't interact with each other and they don't hit each other. But that's kind of a small assumption, because a pretty small effect in reality of the particles hitting each other. Of course, it's going to be accentuated the denser you make the gas and the higher pressure you have it. So they don't collide, so they don't stick, but particularly they don't stick, I think is important. Let's write those both down. So they do, however, hit the walls, because your container is not an infinite volume. They're going to hit the walls. We have to make an assumption about that. And that's the collisions with the walls are elastic, meaning they do not lose any energy to that, right? Energy is conserved in that collision. So you're not going to be, you're not going to be transferring heat very much with that. What other ones I need to do? Obey Newton's laws. Oh, you have there's no particular order to these assumptions, by the way. You have a large amount of molecules or atoms or whatever. So because we're doing a statistical model, and if I said I have 5 atoms, then it's really hard to apply statistics and have it mean anything. But if I say I have 10 to the 23 atoms, then that means that my statistical averages can basically just be taken to be gospel fact. Let's see. I'm looking at a list because I always forget them too. Yeah, those are the big ones, I think. I mean, some other ones be like the duration of a collision is small compared to the time between collisions. So some things I'm seeing when I'm looking at this claim that they do interact, but there are no forces except while they're colliding, but then that means that there's a lot of problems that makes it non-ideal. That's closer to what you'd use van der Waals for. So I would prefer to assume that the particles don't collide, but like our model that we're going to use for our lab that we're going to do shows that they collide. So it's not exactly the ideal gas law, but it's more accurate than the ideal gas law. So I'll just read the another list. So yeah, the gases are composed of separate tiny particles, which are molecules or atoms. Gas molecules are in constant, rapid, straight line motion. The collisions between molecules and the walls are completely elastic. So they're not exchanging energy. There's no loss of energy with the walls. The molecules of a gas have no attraction or repulsion for each other, and each molecule in a gas can have a different velocity. I think I got my cord in the shot there, but oh well. They don't have to have all of a different velocity. We'll write that one down. All right. So, if you stuck with me and got to the end, then congratulations. If not, you can just Google this. But if you didn't stick to the end, I guess you're not hearing this anyways. So, you can't see the volume very well. So, that's my list that I'm going to go with. And if I have to make an update with you guys, I will. But I think this is a pretty good basis. So let's call that one quits, and I'll see you in the next video. Make good choices, guys, and stay safe out there.